All right, good morning. So in this lecture, what you will see, or in the next couple of lectures, what you would see and learn is about defects in solids, diffusion in solids. Then we'll start seeing white thin films. This is the most important, question. So if you talk about thin films, there is no thin film growth, especially when you're dealing with physical vapor deposition without the use of vacuum science or vacuum technology. For that, you need to know about the concepts of vacuum science. What you have learned in the last few classes is about, various types of furnaces, how to create or generate high temperature. It's a big challenge, to get 500 degrees centigrade in a furnace, 1000 degrees centigrade, then 1500 degrees centigrade, 2000 degrees centigrade and above becomes much more challenging. So high temperature is also required for thin film growth. And for thin film growth, if you're using bulk components, for thermal evaporation, you need to vaporize the material by taking it to its melting point. So high temperature is obviously required. And even in the process of sputtering, what you need is, when you are sputtering on any other method, PVD or CVD method, the substrate, the base material on which the thin film grows, when the atoms come on the base material and settle down to their lattice positions, high temperature facilitates the nucleation and growth process. Well, the temperature is required to grow a crystalline thin film is not as high as what it is for preparing its bulk counterpart. Suppose I want to make a thin film of barium titanate, silicon carbide. So to prepare the bulk materials, which are then converted using the thin film growth processes into highly crystalline thin films, the bulk material preparation, the ceramic preparation requires temperatures higher than 1000 degrees centigrade. But when it comes to thin film growth, converting the same material into a crystalline thin film still requires temperature, but temperature is normally not higher than 700 to 800 degrees centigrade. Okay. All right. So when you talk about thin film growth process, vacuum science concepts are very essential, and the thin film growth processes involve the applications of vacuum technology in all thin film growth processes, especially in physical vapor deposition process. Now, I mentioned that there are two categories of thin film growth process. One is PVD, physical vapor deposition. The other one is CVD, chemical vapor deposition. Chemical vapor deposition per se doesn't require high vacuum, but all PVD, physical vapor deposition growth techniques, require high vacuum levels. That's where the science of vacuum science concepts, and how you apply these vacuum science concepts in the thin film growth process, both are very important. Let's start with defects in solids. You have already got some introduction to what are defects in solids. The basic defects in solids are missing atoms, point defects. You also have defects in the form of misplaced atoms that are displaced from their lattice position to non-lattice positions that are called interstitials. Now, what you see in the middle figure here is a crystal, but for me to confirm that it is a crystal, I need to do crystallography, X-ray crystallography. What is a crystal? It's an extension of perfect crystallographic order or structure in 3 macroscopic dimensions. And when this order is there in 3 macroscopic dimensions of the basic unit, that is the building block, unit cell in all 3 crystallographic axes, that means you have perfect correlation of the unit cell at that end to the other end and so on, without any misorientations and other defects between these unit cells. Of course, the basic crystallographic defects are point defects. You cannot have a crystal, perfect crystal. You cannot have a crystal without defects, missing atoms, which are Schottky defects and misplaced atoms or displaced atoms, which are Frankel defects. So extension of perfect crystallographic structure or order in 3 macroscopic dimensions is a crystal, right? And in thin film form, what you see on the left-hand side there, okay? In thin film form, of course, a thin film is also crystalline, but it is limited by its thickness. Length and breadth wise, it's fine. I have a base material on which I can grow a thin film, 1 centimeter square, 1 inch square. And the device grade wafers now are 8 to 12 inches in diameter. But crystallinity is there, but the limitation is thickness. No, you can grow highly crystalline thin films of any material up to a few hundred angstroms. So that's your thin film, where like in a bulk solid, you have a crystallographic order from one end to the other, except that the thin film is limited by thickness. But in a bulk, if I have a 1 centimeter cube crystal, it's a 1 centimeter cube crystal with a single grain, where the crystallographic order, long range order persists all the way from one end to all 3 dimensions. Same order persists here also, but you can also imagine now with the description I've given, there's a limitation on the thickness of the thin film. Okay. Now, on the right-hand side, what you see is a typical example of a polycrystalline material. As I have mentioned earlier, the name itself suggests that you have the material obtained in a form where the name itself suggests that it is polycrystalline. And polycrystallinity is typically denoted by grains and grain boundaries. What you see is a beautiful textbook picture of scanning electron microscopy image of a polycrystalline system, where you have large number of grains and grain boundaries. And these grains are also not of the same size and shape, and they're well delineated or demarcated by these grain boundaries, which are defects. I also mentioned that grain boundaries impede physical properties. They're detrimental to physical properties. That's the reason why we want a polycrystalline material. Polycrystalline material is also easy to prepare compared to single crystals and thin films, right? The easiest is polycrystalline system. I can use the same polycrystalline bulk material to convert it into a thin film. I also mentioned, if you remember, if it takes 1 week to prepare a ceramic like a dielectric, like barium titanate, and this ceramic can be used as a target material in one of the PVD processes, and you can convert this ceramic using a thin film growth process, sputtering process, into a thin film in a crystalline, orderly crystalline thin film, which you call it an epitaxial thin film, in time scales of a few tens of minutes. So the bulk material takes about a few days, and its crystalline counterpart in thin film form takes about a few tens of minutes. But of course, crystal growth is, again, a complex process. The methods used for crystal growth are completely different from that used from thin film growth. And I also mentioned that for crystal growth, you always need a melt. That means you need to melt the material, take it to its melting point, and the starting point, it's melt. And the ease of preparing the same material system in a polycrystalline form is you do not need melts. You need to start at 0.92 of the melting point of the material. So you're not really melting it to get a polycrystalline system. But when you convert this polycrystalline system into a thin film, you are breaking again the entire bulk matrix into its individual constituents. And these individual constituents, atoms, right? So you atomize everything, and you make the atoms to, combine to form the crystalline lattice. So that's why, since the growth process of thin film happens from the bulk itself, since you atomize the whole structure or matrix, so it's a combination of these atoms, atomic scale mixing leads to crystalline formation of thin films at a faster time scale. For single crystal growth, I mentioned that you need to give a lot of time for the atoms to come to their lattice positions. And if you want to avoid these grain boundaries, you need to give sufficiently large amounts of time for crystallization to happen. So a single crystal can be a single crystal is single crystalline. So it has, if I ask you how many grains, this piece of, this could be something like 1 centimeter cube. If I put a scale there, it's a 1 centimeter cube crystal. If I ask you how many grains this 1 centimeter cube crystal would have, once you confirm that it's a crystal, it'll have just 1 grain, not multiple grains. That's why it's called a single crystal. In a similar way, if I get a thin film and confirm it's a crystalline thin film, it will also have 1 single grain. So a thin film formed into high degree of crystallinity, like a single crystal, it is called an epitaxial thin film. The name given to single crystalline thin films is epitaxy. Remember this always. That's a Greek name to describe the crystalline nature of a thin film. So you may ask me, can thin films also be in a non-epitaxial, non-crystalline form? Yes, depending on the growth processes. If the growth processes are not optimized properly, you might end up having thin films also in a polycrystalline form. But that's the whole purpose of growing a thin film, is to get a crystalline form of the material. But it all depends on the process that you use, the parameter optimization. If those are not proper, you end up getting a polycrystalline thin films. You also end up getting a non-crystalline amorphous thin film. Okay, so materials can exist in single crystalline form, polycrystalline form, and non-crystalline amorphous form. A thin film can exist also in all 3 forms. You can have a single crystalline thin film, polycrystalline thin film, and amorphous thin film. Right? This always, you should keep this in mind. So I need a certain amount of temperature for the incoming atoms onto the substrate to form a crystalline growth here. But then if I'm not providing enough thermal energy to the substrate to create the so-called adatom mobility for the atoms to go around and find their lattice positions, if substrate is not heated, no thermal energy is given to the incoming atoms, what will happen is these atoms start agglomerating and leading to the formation of islands, and that's where you see a polycrystalline. So presence of defects in crystals and thin films can influence physical properties, chemical reactivity, electrical conduction, mechanical behavior, and sort of all kinds of physical behaviors are affected. So that's why we want to get materials in highly crystalline thin film form or single crystal form itself. You see, when I call it a single crystal, all the atoms in the entire volume should have perfect periodicity from one end to the other. Same is the case there, right? So single crystalline thin film. But when you come to the bulk counterpart, the polycrystalline material, if you take that grain, a single grain is single crystalline, a neighboring grain is also single crystalline, but you have a grain boundary that separates. And between grains, the orientations of the ensemble of these unit cells can be different, right? So you may have different orientations. All these small crystalline regions are separated by grain boundaries, which are unwanted, which are detrimental to physical properties. I gave the example of how the resistivity versus temperature measured for a typical semiconductor varies between a single crystalline semiconductor form and the same semiconductor obtained in a polycrystalline form. The basic nature of rho versus T is the same, but what changes is the you see additional resistivity coming in when you do this measurement, electrical resistivity as a function of temperature on a polycrystalline thin film. That's because of additional grain boundaries resistance, right? Grain boundaries are more resistive because you have loosely bound atoms. You have terminated crystal structures. It all depends on the grain boundary widths. If you have a polycrystalline thin film, the grain boundary widths are much narrower compared to the grain boundary widths in a polycrystalline material, bulk material itself. Okay, if you look at the material revolution, this is a perpetual process. You have a large number of material systems. You have magnetic materials, you have electronic materials, materials giving rise to dielectric properties, ferroelectricity, piezoelectricity. There are optically transparent materials that find extraordinary number of applications in touch screens, mobile phones, and you have photonic materials, you have biomaterials, you have materials that can convert thermal energy into useful electrical energy. These are called thermoelectric materials. You have mechanically tough materials, materials for automobile, aerospace applications. So, since the past 5 decades, we have seen new materials evolving, new processes evolving to prepare these materials in the best possible manner. Your materials that can be prepared in a highly crystalline form, materials that could be prepared in a crystalline thin film form, and so on. Right? Now, I also mentioned that we are fortunate that all these hundreds of thousands of materials exhibiting all these interesting physical properties crystallize into 7 crystal forms, 14 Bravais lattices, and about 230 space groups. So that's where I keep emphasizing that a basic knowledge of crystallography is very essential. And these are examples of natural crystals here, fluorite, azurite, rhodochrosite. Each of these crystals, they're all colored, and I'll come to that point why how crystals can be basically colored, but they all possess specific crystal structures, like what you see here. So that's where by looking at them, you can't find out which crystal structure they possess. But of course, by doing crystallography, I'll be able to distinguish the hexagonal crystal structure of emerald to the tetragonal structure of wulfenite. No? So if I shape all these crystals into a typical form, all of them look shiny, of course, with different colors. Colors come because of doping and existence of defects. We'll see how that happens. But then the exciting thing is all these crystals, there are millions of naturally occurring crystals exhibiting various beautiful colors, properties, physical properties, optical properties, magnetic properties, but all of them belong to one of these 7 crystal forms and one of the 14 Bravais lattices. And of course, the space groups could be different. So what are structural defects? You've seen grain boundaries already. You also have serious defects that are dislocations, vacancies. These are point defects, the basic, missing atoms, Schottky defects, and displaced atoms, the Frankel defects. You also can have defect pairs. But today's technology, the physics of defects is very interesting. We call it the physics of defects. There's so much to understand about the formation of defects, how to control these defects. Point defects cannot be avoided because you cannot have perfect crystals. Grain boundaries can be avoided by transforming bulk materials into thin films and single crystals. Okay. Now, these are you've seen this already. A typical example, textbook example of grain boundaries, grain boundaries, and you see that even the voids. This is the typical problem in a polycrystalline material. Voids means completely missing material, right? So these are all unwanted. These are all detrimental to physical properties. In addition, the serious crystallographic defects are you have edge dislocations, screw dislocations, and you have stacking faults in most of the lattices. Okay, crystal growth also, when you try to grow single crystals and thin films, if the process parameters are not properly optimized, you see stacking faults. These stacking faults could be from few millimeters, micrometers to nanometric levels. But let me tell you something interesting. The physics of these defects is so interesting. We know that grain boundaries are unwanted, detrimental to physical properties. But if you control the grain boundaries, we can do some very exciting physics. It's called the grain boundary physics. And you can also envisage interesting applications. Control grain boundaries is a process that that is used in tunnel junctions. The whole concept of magnetoresistance, comes from artificially grown layers. That means I controlled the boundary between these different layers. That is meant by controlled grain boundaries. So magnetic tunnel junctions, it all started from GMR devices, chain magnetoresistance devices. Now you have tunnel magnetoresistance devices. All that is based on controlling grain boundaries. Then vacancies, say for example, point defects, inevitable, and you also have defects in the form of dopants. You replace one lattice atom by a small percentage of a foreign element, without which physical properties will not change. For example, a pure silicon is not a good conductor. Of course, we know that it's a semiconductor. To get silicon to useful semiconducting properties, you need to dope it and make it a p-type or an n-type semiconductor. So without doping, that means without inducing defects into silicon lattice, you will not see enhancement in conductivity. So today we have gone to a level where if you have controlled defects, these defects can be used for quantum computing. For example, defects in diamond. Intentionally dope defects in diamond by replacing carbon by, say, nitrogen, and by creating these nitrogen vacancy pairs, Frankel pairs. This is exciting. You can use them for creating quantum bits. So to say the least, defects are not all that bad. You control and control the physics of these defects, and you can uh, do rich physics experiments, understand a great deal of physics involved in the process of how these grain boundaries can contribute to um, various useful applications. And similar is the case with controlling vacancies and point defects. Okay, so grain boundaries are defects. It's interface region between two single crystalline grains, and the atomic bonding terminates at the grain boundaries. So at the grain boundaries, you have more loosely bound atoms compared to grains. In the grains you have the regular formation of the lattice, which is not the case when you reach the grain boundaries. So again, grain boundaries are heterogeneous regions. Diffusion, phase formation, precipitation, corrosion, impurity segregation, all these are due to the presence of grain boundaries. Electronic transport in metals, semiconductors, and materials in general is impeded through increased scattering at the grain boundaries. So that's a whole reason why we want to get materials with minimal number or low volume of grain boundaries, or completely eliminate them by getting the metals or by getting the materials in single crystalline form or thin film form. By the way, you should understand that it is not easy to grow single crystals of metals. Okay. Now coming back to this, I've shown this slide earlier. Electrical conductivity is such a simple property where I take the material in the form of a wire or a rod or a slab with a known cross section. I pass a known current through it, measure the voltage drop, and then if I know the cross section area and the length of the conductor, I'll be able to find electrical conductivity. And just by doing this simple experiment, I'll be able to distinguish all the way from metals. As you can see here, you have a range of metals in terms of electrical conductivity. They're good metals, noble metals, and not so good metals, right? So this range itself is varies over 4 orders of magnitude. But when you come to semiconductors, you see that the range is over 10 orders of magnitude. You see between silicon and doped silicon, the conductivity changes by almost 5 to 6 orders. That's the power of doping, and when you come to insulators, you see the conductivity range varying by almost 10 to 12 orders of magnitude. All put together, this simple measurement called electrical conductivity can give you, conductivity variation over 27 orders of magnitude. I don't think any other measurement can give rise to so many orders in change of magnitude while measuring one single property called conductivity. Of course, the measurable property is resistivity. The inverse of that is conductivity. So you see the range of conductivity ranges of metals, semiconductors, and insulators is given here. The conductivity, the unit for resistivity is ohm meters or ohm centimeters. The inverse of that, ohm inverse, meters inverse is the unit for conductivity. It's Siemens per meters, right? The fundamental unit is Siemens per meters. So you have a conductor, a typical conductor has almost linear resistivity behavior. It's actually T-square kind of a behavior, and the resistivity goes as T power 5 at low temperatures. This is a semiconducting behavior of rho versus T, and a superconducting material shows a normal state resistivity, right? And linear behavior, and then at the onset, it starts losing its resistance, and it offers no resistance to the flow of current, and the resistance vanishes, and that is a typical superconducting behavior. Yeah, this is what I was mentioning about. A non-superconducting metal shows a behavior like this, a T-square behavior. This is also called um, a Fermi liquid behavior. For a superconductor, if a normal metal is becoming a superconductor, the point where it loses its resistance, the normal state resistivity is almost retained, but you get zero resistivity. But there are also unconventional superconductors, which are not metals to start with. They acquire metallicity by doping. So those superconductors that show a normal state resistivity, which is a linear behavior down to the superconducting onset, and then you get zero temperature. Of course, superconducting transition is also confirmed, has to be confirmed by the Meissner effect, because a superconductor, when it is put in a magnetic field, the magnetic field lines flow through the interior of the superconductor, but the moment it reaches the superconducting state, the TC, that temperature, the magnetic field lines are thrown out of the interior of the superconductor. So the magnetization B is zero inside a superconductor. The result is this beautiful Meissner effect. So if you have a bulk superconducting material, and if you bring a magnet close to this superconducting material, in the superconducting state, because of the flux, magnetic flux lines expelled out of the superconductor, you see the magnet hovering on top of the superconductor. That's called the well-known Meissner effect. So this normal state metallic behavior leading to the loss of resistance is also confirmed by the magnetic measurement, where a superconductor gets into what is called a perfect diamagnetic state. So in addition to metals, semiconductors, insulators, superconductors also would have defects. And these defects would also influence the superconducting properties. Okay. So what are these defects? You know, for historical reasons, many point defects, especially in ionic crystals, are called centers. You know, for example, a vacancy in many ionic solids is called a luminescent center, or it's called a color center, or an F center. F stands for Faber in color in German. All right. But what are these defects? You know, what you see on the right-hand side is a nice natural translucent color of a quartz crystal. Okay, you can also grow quartz in the lab frame. Okay, but whether you grow a crystal in the lab, or you get a crystal, a naturally occurring crystal, point defects are always there. So you can't have a perfect crystal like the image I'm showing on the right top here. This is an idealistic case. No, there are no perfect crystals. Crystals always will have point defects. So these open circles are called atomic positions, right? So you see, they're all periodic, right? In physics, we learn about the periodic potential and all that. We talk about Fermi gas, you know, the electron gas. You know that you have electrons associated with these atoms. In some cases, these electrons are localized. In some cases, these electrons are itinerant, giving rise to the process of conduction. And it's the same electron that gives rise to a magnetic property also. Everything comes from the lattice, right? It's a basic building block. So a solid is made up of lattice plus electrons. So this is a lattice. And here you see the lattice atoms are all periodically arranged. So the periodic potential that we talk about in solid state physics, the periodic potential comes because of the periodicity of the lattice. Electrons are not periodic. The electrons attached to the atoms are not periodic. They are the periodicity comes because of the periodicity of the lattice. So any deviations or perturbations in this periodicity, right, at the atomic level, how do you determine that? That's where crystallography is so important. Now, if you look at a periodic arrangement of these atoms, right? I said there's no ideal case. One of the most common defects is the vacancy, missing atom. Okay, so that is called a Schottky defect. I'll come back to this, but let's start with missing atom. So atom completely missing. It is obvious, because there is a certain amount of energy required to knock an atom out of the lattice, and this energy you're providing, because the crystal growth process or thin film growth process is obviously a high temperature process. So I said a crystal can be grown only when you start from its melt, the melt of the constituent material. So when you're melted the compound, right, there's always a possibility of losing certain atoms. You're vaporizing atoms. You're losing atoms. So if you lose some proportion of atoms in the molten state, right, and when the lattice forms, you see lattice depleted of some atoms. Yeah. And the other process is there's also sufficient amount of energy available for these atoms to move from their lattice positions. These are all the lattice positions to a non-lattice position. You see, that's a non-lattice position. Yeah. And that is called an interstitial, which is also called a Frankel defect. So Schottky and Frankel defects are the two most common defects that you find in crystals. But how do you visualize them? Today we have processes to visualize point defects, Schottky and Frankel defects. Now I can replace one of these atoms, lattice atoms, by a bigger in an ionic radius or a smaller atom, as what you see here. This is also possible. These are called substitutional atoms. So I'm replacing a lattice atom by a substitutional atom, which could be bigger or smaller than the lattice atoms, obviously, because if the foreign atom has to have the same size as the lattice atom, I have to substitute it with the same atom. That means if this lattice is made of silicon or germanium, right? Each element in a periodic table has its has a different ionic radii. So the replacement of the constituent lattice atoms can be done only by smaller or larger atoms. So the lattice can take certain amount of size variations, right? And that is determined by the Madelung energy of the lattice. A Madelung energy is a very important concept in crystal formation. Thermodynamically, when you say a system cannot take a foreign atom, more than a certain size, or a foreign atom more than a certain percentage of concentration, it's because of the stability of the lattice, the disruption in the stability of the lattice. And that disruption in the stability of the lattice is determined by what is called the Madelung energy. So one has to do a lot of calculations, find the nearest neighbor atoms, then you find the Madelung constant, and every crystal system has the Madelung energy. That will tell you the Madelung energy has to be as low as possible if a given crystal lattice has to be stable when a foreign atom comes inside, right? It's like our body immune system taking certain amount of external entities, viruses, bacteria, before the system starts showing other unwanted signs. So a lattice is also like that. It can take a certain amount of external impurities. So I can replace the lattice atom by a larger atom or a smaller atom. Now, what happens when I replace a lattice atom by a larger atom or a smaller atom? Obviously, when so you see the periodicity there. I'm replacing one by a larger atom. So locally, there is an expansion of the lattice, right? And in this case, when the size of the incoming atom is smaller than the size of the lattice atom, so there is a lattice contraction. Not beautifully. And you see, typically in semiconductors, if we want to bring about changes in electrical properties, for that matter, this is called doping. Doping can bring about changes not only in terms of changes in electrical properties. You see, doping brings interesting magnetic properties. The reflectivity of the material can change. The dielectric properties can change, right? Doping can cause interesting physical property changes. But then the dopant levels are very, very small. In semiconductors, you start seeing these interesting changes in electrical conductivity when the foreign element is present in concentrations of not more than 1 to 5 to 7 atom percent, to maximum in some cases 5 atom percent. But most of the changes happen between 3 to 5 atom percent of the dopant getting inside the lattice. This is very small. 3 atom percent is out of 100 atoms, 3 atoms are the foreign atoms. But you see, but these 3 atoms out of 100 atoms are bringing about a great deal of change in the physical properties. That's the interesting part about doping in solids. Okay. Now, what happens this local expansion and contraction of the lattice? How do you determine that at that atomic level? After all the neighboring unit cells are fine, but wherever an atom is replaced by a smaller, bigger or smaller atom, there's a local distortion. That means what? So when I say lattice expansion or contraction, so the lattice length or lattice parameter is changing. And this lattice parameter change can be observed using crystallography. And that's where diffraction plays such an important role. Okay. So, and the third kind of defects are the Frankel pairs. No? So you have you have interstitial atom and a vacancy, and sometimes these two form a pair. And a vacancy or an atom replaced by a larger or a smaller foreign element, right? This and a vacancy can also form a pair. And in today's technological applications, I told you the best example is the diamond, where you have nitrogen replacing carbon. Diamond is lattice is made of carbon atoms. Nitrogen replacing carbon. like boron replaces silicon in silicon lattice, nitrogen replacement in carbon brings about some additional carriers into the lattice. It can transform even this insulating diamond into a good conductor. And with boron doping, it becomes even superconducting. But nitrogen doping can have many positive implications. It can bring an electron into the lattice. It can also form a pair with a neighboring vacancy, forming what is called an NV center. And that is the basic quantum unit with which you can do a lot of quantum information studies. But the physics of NV centers is quite exciting. You see, that's where I tell about controlling these defects is going to be very exciting in terms of learning the physics of all this. Yes. What is this you're seeing here? That there's a crystal here, but these two crystals are colored. And this coloration comes in ionic solids because of the presence of color centers. Okay. So watercolor centers we'll see in tomorrow's class.